At Broad Institute, raw sequencing data is not saved in FASTQ format. Instead, it's saved in unmapped BAM file. This is because FASTQ does not have a place to store all the metadata information. But in the unmapped BAM file, or even mapped BAM file, the header section can be used to contain all the metadata information. And let's say that we have been brought onto a new project. We'll be analyzing some particular variants in chromosome 20, and we are given an unknown BAM file. How do we know that what has been done on these files already? First, let's use the SAM2 to show the header section of this BAM file. SAM2's view -H is to view the header section. Mother.bam is the file, and we want to pipe the output, not to show all the output, but just grab the one with the regroup information. Oh, sorry, it should be SAM2's view. Okay, so we can see the sample ID and the sequencing platform, PU, the library, and the sample name is NA12A70A. And what if we want to know what program has been used onto this BAM file? Similarly, we can grab the PG program tag. So we know that the file has been first run the BWA MAM alignment 2, and that is the command used to do the alignment. And then it's run the mark duplicate by the Picard program. And then it used the GATK print reads to do the calibration, and the indel realigner to realign the reads. So by looking at those PG tags, we can know the history of the BAM file. Right after read mapping, we need to do mark duplicates. Duplicates are the non-independent measurement of a sequence fragment. It has to be removed to access the support for alleles correctly. So this is just one type of the error. There are also some other type of errors that we need to consider during the variant calling process. For example, PCR artifacts, the error introduced in early PCR runs, or the sequencing error, that is the wrong base callings, or the mapping errors, that is a map to the wrong location in the reference, especially for multiple mappable reads. So here, a duplicate must be removed, because from this view you can see if one SNP is from the PCR duplicates, but not from the original DNA copy, DNA molecule, then our interpretation of this SNP will be pretty wrong from the actual truth. So where does the duplication come from? There are mainly two resources. One is from PCR duplication. That is, the PCR replicates this molecule many times. The second source is the optical resource. That is on a tile or two adjacent tiles. If there is a single cluster of reads that is part of two adjacent tiles, then this single cluster of reads will be read once from one tile and the other, and one more time from the other tile. Then initially it's only one read, but now it becomes two reads. So how do we identify duplicate reads? If it's a PCR duplicate reads, then we can identify the after alignment. It's like this picture after alignment, if there are several reads that have exactly same starting point and ending points, then very likely, and also if the sequence steps is not that deep, then very likely this is caused by PCR duplication, but not the real by chance there are two exactly same DNA molecule. And if it's an optical duplicates, if the first n base, for example, first 50 bases of the sequence are exactly same during the base calling, then we can just disregard this read. And how to run mark duplicates in, we use part2. We can copy and paste this command. Okay. Okay. We can see the result has a file ending with dupe matrix. We can look at this file for the mark duplication statistic. Let me look at it. So usually we look at this number. It's the percent duplication. So in this, for this sample, there is a 6% duplication, which I think is normal. Usually we can see anywhere between 4% to 10%. Okay. But I have to emphasize that remove duplicates for single end reads for deep sequencing data has a high false positive rate, because if we sequence deep enough, then there are so many reads cover particular region, and the chance that two exactly same DNA molecule fragments cover the same range, have exactly same starting point and ending point, are very high. It's very likely you mark the wrong duplicates. It's not a PCR duplicate, but a real DNA molecule. And this is fine for SNP calling as long as you can get enough coverage. For example, 40x coverage, you can remove duplicates, that's fine. But it's very dangerous for RNA-seq or chip-seq. We know those for those application is most of the application for RNA-seq and chip-seq is for quantification. So you can mark duplicates, but you don't, it's recommended not to remove those duplicates. And there is a great blog by Eric. I suggest you to read about the math behind the duplicates. And also there is an alternative tool for marking duplicates, the SAM Blaster. Okay, next we'll talk about the RNA-seq data pre-processing step. This is only for RNA-seq. Remember I showed you the blue line that is particular for RNA-seq for the intronic region. We have to split this line before we call the variants, and that's a step called the split and trim step. So I listed the command you can use for this step, but I will not run it here. So this is before and after split and split and cigar reads. It's just this blue line disappeared. So next step, base recalibration. This is need to be run for both DNA-seq data and RNA-seq data. I also listed all those commands here. The first step is to build a base recalibration model. So it depends on the data as a whole, the whole data. It look at it gets or look at which sequencer you are using, and what is the particular systematic errors this sequencer has in base quality scores, and this BQSR will correct for that quality score. And after the recalibration model, it will generate a recalibration table, and you put the recalibration table as an input file, then it will give you an output file after the recalibration. And the second, you can get the second round recalibration table for analyze the covariance. And you can also get a quality control plot. So this is the PDF file I got when I ran those steps. But compare before and after. Pink is before, after is after the base. After is blue. There is not much difference for this particular data set. And here I also show you an example when the BQSR improve significantly. The before calibration, the reported quality and the empirical quality correlation is not very well. And after calibration, the blue line, it's just a straight line, performs pretty good. And the same as the original RMSE, root mean square error, and the recalibrated RMSE performs much better than the original one. And this is the difference, the accuracy between the empirical and the reported quality score. So anyway, comparing to those good examples, our sample, the RNA-seq data, I use the RNA-seq data set for this recalibration. This RNA-seq data didn't perform very well on the recalibration data set. So can you guess what's the reason for that? Yeah, you can think about it. And you can email me if you have any question. Okay, so here is a summary of the GATK data preprocessing workflow from the raw data to map to the reference, mark duplicates, base recalibration, and we now get analysis ready reads. And for RNA-seq data, we have one more step between the mark duplicates and the base recalibration, that is split and trim.